Hi, everyone. Welcome to chapter 3. This is a new chapter, and we are introducing you to logic and what does it mean to work with logic. The first thing we need to do is to talk about statements and quantifiers. So statement and quantifiers is what we're going to go over in this recording. So section 3.1 are statement and quantifiers. What are the objectives of this lesson? The objective of this lessons are to distinguish between what is a statement and what is a non-statement. Compose negation. What is a negation of a statement? What does that mean? We are going to be translating words and symbols together. We are going to be interpreting statements with quantifiers and the form of negation. And we are going to be looking at true values of statements involving quantifiers and numbers of sets. So we're going to be learning what are the sets of numbers. So numbers have different sets, and we're going to be looking at that in this recording. To first talk about a statement, you need to understand the definition of a statement. A statement is a declarative sentence that's either true or false, but not both. So we could say, today is Saturday. That could either be a true sentence or a false statement, but it can't be both. So you can't be a Saturday and a Sunday at the same time. That's an example of a declarative sentence. A compound statement. What is the difference between a statement and a compound statement? Well, a compound statement may be formed by combining two or more statements. The statements making up a compound statements are called a component statement, using various logistic or logical connectives or simply connectives. What are connectives? Words such as and, or, not, if, and then. These can all be used forming a compound statement. So in this example, in this recording, we're going to see different types of statements, both compound and simply statements. So we are going to move on to the next slide. So making sure that you're highlighting what types of connectives do we have. So these are both. You can call them logical connectives or just connectives. So let's look at the first set of questions. Example 1, deciding whether a statement is a compound or not. Decide whether each statement is compound. If so, identify the connective. So we need to identify which is a connective. The first letter A says, you can pay me now or you can pay me later. Well, and then B is my accountant works for Ernst and Young. Well, let's see which one is a compound. Well, A says you can pay me now or you can pay me later. Well, you're talking about two different things. So A, it's going to be a compound because you're separating it by a connective, and the connective is the word or. Now, my accountant works for Ethan and Young, but this and is not a connective. This is not compound because you're not comparing different things. These are just people. So as my solution, B is not a compound since it's part of a name and it's not something logical. It's not a logical connective. So, and it's not a connective, and letter B is not a compound statement. Part A it is because your connective is a NOR and you're splitting up a logical thing. So you're talking about you can pay me now or you can pay me later. That is something connective, something that has logical meaning. Okay, so hopefully we have this down, which is slide 7, looking at the example of a compound statement. So today is Sunday and it's hot. That is a compound because you're connecting two things. You're connecting that it's a Saturday. So today is Saturday and it is hot. So this is my connective, and you're connecting both that it's Saturday and it's hot. You have a logic meaning. So part C would also be compound, and the connective would be an and. What about a negation? The negation, Max has a valuable card. The sentence is a statement because you're declaring something. The negation would be something that you are negating. So Max does not have a valuable card. So has to not have or does not have. That would be the negation. So the negation of a true statement is false, and the negation of a false statement is true. See how powerful that is? The negation of a true statement is a false statement, and the negation of a false statement is a true statement. So we're going to look at the negations of different examples in the next slides. So let's continue. Form the negation of each statement. So the city has a mayor, that's a statement. So you want to negate it. So the city does not have a mayor. Does not, or does not, or have not, does not have a mayor. Whereas the moon is not a planet, you change it to something false, or something true. The moon is a planet. So you're negating. The city does not have a mayor. That's the negation. The moon is a planet because since it was not a planet, now it is. You're negating the original statement. So example 2 is forming negations. You're negating something. So if I would say today is Saturday, today is not Saturday. I'm not saying what day is it. I'm just negating that it's not what I said. So you are negating a statement. It's saying today. So for these couple of days, it's been really hot. I would say these few couple of days have been cold. Well, you'll say the few couple of days have not been cold or hot. So it would be something that you're negating. Now, the next part is finding inequalities of symbols. So let's look at the value. Use the following inequalities for the next example. When we say A is less than B, if we notice, so less than, A is greater than B, A is less than or equal to B, and A is greater than or equal to B. We're going to be using these as well when we do negation, so please be careful. So when I can also negate a symbolism. So I can negate a meaning, like a sentence, and I can also negate a symbolism. So making sure that you are aware that I can change both. I can negate both a symbol and a meaning. So yes, I can negate a symbol. Okay. How? Well, switching the order. And you'll see that very soon. Let's look at this one. Give a negation of each inequality. Do not use a slash symbol. So this is x is less than 9. So if it's not less than, it would say now x is greater than or equal to 9. This is special. So you are including a greater than. So you're flipping the inequality, but you're also adding the equal to. And adding an equal to symbol. So you need to make sure that you are adding that. So if it was x less than 9, now it's x is greater than or equal to 9. Now look at B. If it's a greater than or equal to, well, we'll say that this is 3x minus 2y is strictly less than 12. So the inequality will not hold because you're negating. So when you negate a symbol, you remove the equal to in this case. So instead of adding, you're removing it. So it's going to be 3x minus 2y is strictly less than 12. And that would be my solution when I negate inequalities. So when you're doing your homework, you need to make sure that if your original is a less than and you're negating it, you need to flip it and add that in that equal symbol. And if you're negating a greater than or equal to symbol, you are removing the equality symbol. Okay, so making sure that depending on what you have, that's what you're going to be doing. All right. Now let's look at the symbols. What are the connective? We already saw some connective logic words. To simplify work with logic, we use symbols. Statements are represented with letters such as P, Q, or R. So these are the typical letters that we use, while several symbols for connectives are shown below. So when we see an and symbol, the and symbol corresponds to the caret that goes upward. This means a conjunction. Or looks like a V, and that is called a disjunction. So you are splitting them. So you're not doing a combination, you're actually doing a disjunction. And when you have a not, it's this little squiggly line that looks like this. This is a not symbol or a negation symbol. So you're negating. Whenever you see this little tingling line, you're actually negating the symbol. So please make sure you have this in your notes. You want to create this table, and you want to make sure that you're memorizing the symbols and what type of statements you have. An and will be a conjunction, an or will be a disjunction, a not will be a negation. So let's do the following. Let P represent it is raining, and let Q represent it is March. Write each symbolic statement in words. So we're given symbols and they want words. So P or Q. So first of all, identifying that this symbol, this connective symbol is a disjunction or. So this is P or Q. Well, we know what P is. So it says it is raining or it is March. So it is raining, that's P, and let Q represent it is March. So P or March. So it is raining or it is March. Now, this is a different one. This looks like this. This symbol is removed. So this is a little squiggly, and this should look like this. So let's fix our typo first. So this is a typo. So this means that this negation is going to distribute here, here, and here. So the negation will be not P. So if I negate my or, that means I am an and symbol, and then not Q. So this would be, it is not raining. And, oops, so raining. Let me go back. It is not raining. And it is not March. And it is not March. So what did I do? Well, this symbol distribute to both P, well, to everything, P, the symbol, and Q. So it is not the case that it's raining and it is March. So this technically negated, it is not the case. So it's not raining and it is not March. So it is not the case that you have that it's raining and it is not March. So what we did was we distribute the negation to the if this was an original value of V, now it becomes an or. So the and becomes an or. I negated P and I negated Q. So first let's fix. So this part is incorrect. So let's fix our solution, because we had the initial symbol of my slide was incorrect. So make sure that we fix our typo. on the notes. So we had a negation of a P or a Q. That means I'm going to negate Q. I'm going to negate the symbol and negate Q. So it is not raining and it is not March. Now the quantifiers is, and this is I think, a few more slides to go. What are quantifiers? So quantifiers are words that represents all, each, every, and no, which are called universal quantifiers. So there's universal quantifiers that are called all, each, every, and no, where we have existential. So existential are the words like some, there exist, at least one. Those are called existential. So we combine both universal quantifiers and existential quantifiers. So quantifiers are used extensively in mathematics to indicate how many cases of a particular situation can exist. How can we negate quantified statements? So if it's all do, then some do not. That would be the negation of all do. Some do, that means none do. So be careful. So if it says all, then some do not. If it's some do, that means none do not. And then let me add some, none do not, or none do, sorry. None do. So from some to none. So if some, that's the statement, then the negation will be none. If the statement is all, then I'm going to do some. Okay. So let's make sure that we pay attention to the statement and the negation. And how do we negate? So we're going to look at the examples here. So if it says some cats have fleas, so from some do not to some do, we would have, oops, no cats have fleas. That would be the negation because I'm going backwards. So if from none to some, so there's the negation. From some do to none do. So no cats have fleas. Some cats do not. So some cats do not. Oops. So now I'm here. Some cats do not. We'll go to the negation, which is all cats have fleas. Again, we start with the some cats do not. So I'm looking at the negation. I'm looking up here. So I'm looking at some do not. I'm going to look at the negation. I'm going to go backwards. Now it says all do. So all cats have fleas. And the last one is if my negation, it's no cats have fleas. So if no cats, that means that some cats have fleas. So I'm going backwards. So if none do, then some do have fleas. So there it is. So some cats have fleas and no cats have fleas. So I'm pretty much going backwards and using this statement here, from statement to negation, negation from statement. I'm going back and forth and solving using that exact table. So again, some cats have fleas. I started with some do. That means none do. If it says some cats do not, so some do not, that means all do. So I'm going backwards. And then if no cats, so it says none to some do. So some cats do have fleas. And that would be the solution of example 5, which means forming negations of quantified statements. So this is very important. Okay, so there's going to be a question on your knowledge from forming negations of quantified statements. For the last few slides, we want to find the sets of numbers. So look at the natural numbers. These are counting numbers. When you start counting when you're young, you start with 1, 2, 3, 4, 5, 6. Now where whole numbers are similar to natural, but the difference is that a whole number includes 0. So this one includes 0. Integers include positive and negative and 0, plus and minus and 0. Rational numbers includes fractions, but not irrational numbers, like the square root of 2. So irrational numbers would be like a square root of 2, square root of 3. pi, some numbers that cannot be expressed as a quotient. And then we have real numbers that can be anything. So this is all numbers, including rationals, including irrational, sorry. So real numbers is absolutely everything. Now, deciding whether the quantifiers of the statements are true or false. So for example, there exists a whole number that is not a natural number. Well, if we look at the whole numbers, there exists a whole number that is not a natural? Well, yes, 0. That's true. So this is true. Oops. This is true. Let me extend this. This is true. So 0 is a whole number, but not a natural. So yes, 0 is a whole number, but not a natural. Remember, natural numbers are the counting numbers like 1, 2, 3. It does not include 0, whereas the whole numbers do include 0. And then it's saying every integer is a natural number. Well, be careful. What are integers? Integers are 1, 0, 2, -1, -2. Well, -1, -2 is not a natural number. So this is false. So I found something that can negate it. So the first one, A, this is true. And B is false because negative numbers are not natural numbers. All natural numbers are integers, but not the other way around. So be careful. So integers are much bigger than natural numbers. And that is it. That is the end of section 3.1. Hopefully, as you are doing your homework assignments, you're understanding a little bit more on quantifiers and different statements, connectives like and, or, if, then, these examples that we went over, how to negate them, how to negate quantifiers, universal quantifiers and existential. So there's 2 types. Alrighty, so that is the end of section 3.1. I will see you until the next recording. Have a wonderful day. I'll see you next time. Bye.